In this video, we're going to look at Chapter 18E on modeling with the sine function. Let's consider a hypothetical situation like the average monthly rainfall of a given location. If we were to look at this data on a coordinate system, it might look something like this. And so on the x-axis we would have time in months, and on the y-axis we would have amount of rainfall, let's say in inches. So notice how this data sort of looks like a sine curve, right? And we could roughly fill in a sine curve that would be repeating. And notice how not all of the data points fit exactly on that sine curve, but it's pretty close. And the closer the real data set is to actually being a sine curve, the closer those data points will be to the line. This is called modeling, and it's a very useful tool for helping us predict future events in the natural world. Remember from our last video that we can transform the standard sine function, which is y equals sine of x, to a more general case that looks something like this: y equals a sine of b times x minus c plus d. And remember, each of these letters, a, b, c, and d, have an effect on the graph of the sine function. The first of these that we should actually look at is d. And that's because d comes from the new primary axis. Notice that my curve here is entirely above the x-axis. That means my primary axis has been shifted up. And I need to find the new primary axis. So d would be something like this. And d, we would just look at where that line crosses the y-axis, and that's my value for d. Once I know that, I can look at a, which is the amplitude. And remember, a is going to be the height above the primary axis to the maximum, or the height to the minimum below the primary axis, and those two values should be the same. So this is a. B is the period, right? So how long it takes for a graph to repeat itself. So if we were to draw that, we have one really clear point, which is a maximum here, and another really clear point, which is a maximum here. And so the distance between those 2 points is the period. And remember, we can calculate the period by dividing 2 pi by b. Now, when we're modeling, more often than not, we're going to know p instead of b. Right? P is how often the graph repeats, and that's something we can actually look at on the graph. So we should rearrange this equation to find b, and quick little algebra move right here gets us an equation for b. So d I can read off the graph, a I can essentially read off the graph. Remember, a is, let's say, the max minus d, or d minus the min, either one. Or, if we want to be a little bit more precise, we should we should use the maximum and the minimum. And then just divide those by 2. And sorry, I lost a few things here when I hit the back button, so I'll just quickly rewrite those. Okay, so the more appropriate method for finding A is max minus min over 2. And then the last thing that we need to look at, and this can be the most confusing, is C. And C is we can find at this point we call M. And we need to find that point M before we can find C. Now M, notice that in a normal sine function, we'd start here at the origin, and then we'd go up and down and up again. M is that point, that origin point that's been shifted. In this case, it's been shifted over and up, right? But we're more interested in how far over it's been shifted. So M is a point that's on the primary axis, D, but it's also a point where the graph, the sine curve, is going up. Right? Notice there's a point here that's on the primary axis, D, but the sine curve is going down at that point. And this is not how the sine curve starts normally. So we want to choose the point where it's going up. We want to choose the first point, M, on the primary axis, D, where the sine curve is going up. Once we've done that, finding C is easy. We just take the length between the origin, or the y-axis, and where the point M is on the new primary axis. That distance right there is C. Now once we have all of these, A, B, C, and D, we can write an equation or a model for the natural phenomenon that we're looking at. One more thing that I should mention is to find D, we can just sort of read it off the graph, but if you want a more precise method, like we have for the other variables, D is a lot like A, but it's a plus sign. We have the maximum plus the minimum divided by 2, and that gives me a really quick way to calculate what D is. So I don't have to really guess where the middle is. I can just use this equation. So I have equations pretty much for 3 of the variables, and then C I just need to read off the graph. And we'll go through a few examples in a moment. In this slide, I just want to give you a quick definition of what a periodic phenomena is. And that is any real-world situation that can be, or that exhibits, periodic behavior. If a real-world situation exhibits periodic behavior, then we can use more often the sine curve to model that behavior and predict future events. Here are a few examples of periodic phenomena. In all of these situations, average daily temps, depth of water in a harbor due to tide, and the number of daylight hours at a specific location are repeating or periodic, because they repeat, and with a pretty regular pattern. And if they do that, we can model them with a sine curve. Let's take a look at an example now. Let's say we're interested in predicting the mean monthly temperature for the year ahead. Well, if we have collected data from the previous few years, we can model this data, because it's periodic, with a sine curve. So I have my months and my mean temperatures, and I've plotted them on a graph here. The x-axis is time in months, and the y-axis is temperature in degrees Celsius. And you can see by the graph that this is a periodic phenomenon. The model in this case is actually going to be the equation, and it's the same equation that we've been using. A sine B T minus C plus D. And in this case I'm using capital T for temperature and lowercase t for time in months. Otherwise the equation is exactly the same. So if I can find A, B, C, and D, I have my model. And then I can take that equation and I can plot it on top of the graph and see how closely it fits. So I need to find A, B, C, and D. Well, remember A and D are really easy to find. I just need to locate the maximums and the minimums. So I go up here to the table and I see that the maximum temperature is in January. This must be somewhere in the southern hemisphere, right? Maximum temperature is 21, and the minimum temperature we see is in July, and that's a temperature of 8. So I know my max and I know my min, therefore I can find D. D is max plus min over 2. So D is simply 21 plus 8 over 2, which is 14.5. A is going to be max minus min over 2. So that's going to be 21 minus 8 over 2, and that's equal 6.5. Remember that we have an equation for B. B is equal to 2 pi over P, where P is the period. So period is how often this data repeats. Well, if I look at my first max and my second max, I see that they're both in January. That means this data is repeating once a year, or in terms of our time units, it's repeating once every 12 months. So B is 2 pi over 12, or simply pi over 6. The last thing that we need to find is C, and remember, to find C we need to find point M. Well, point M is going to be somewhere on the primary axis, and the primary axis is 14.5. Right, so I could go up here and graph 14.5. It's going to be slightly below this line right here. It's going to be a little hard to graph. So what I could do is go look at the data and see if there's a 14.5. Oh, look at that. We're lucky. There is a 14.5. And further, notice that it occurs on the primary axis when the graph is going up, when the sine curve is increasing. So that's exactly the point I want, point M. Point M occurs in October. So we need to find a value for October. Well, we can label the months. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And it just so happens that in this example, 14.5 occurs in the 10th month. So that is what our C value is. C equals 10. And if we put this all together, we can write the equation or the model. Let me use a different color here. T equals A, which is 6.5, sine B, which is pi over 6, lowercase t minus c, which is 10, plus d, which is 14.5. And this is our model. Now this is an equation I can graph in any graphing program on my calculator, my iPad, my computer. If I do that, I'm going to get this graph. Notice a few things here. The line, it fits really well to the data, but if we look closely, there are a few points, namely March and November, that are not exactly on the curve. And that's okay. This model is our best guess, our best fit at predicting the data. And once I know this, I can go out here in the future and predict what the mean monthly temperature is going to be during the next June, July, or whatever month I choose. In this next example, we're going to look at modeling the low and high tides in a harbor. And so again, I need to collect a little bit of data. But this is very useful in the real world because once we've modeled low and high tides, we can predict when those times will be and when it's safe for ships to come in, when it's safe to go surfing, all those sorts of things. It's really useful to know low and high tides. So I can plot some data. I know that the first low tide that I'm looking at is 7:57. Okay, so I'm going to plot that one on Saturday. Then I'm going to look at the high tide on Saturday, the first high tide, which is at 2:29 p.m. So I plot that point there. Then the next low tide on Saturday, which is 8:24 p.m. And the first high tide, which is going to be on Sunday morning, 2:42, 8:41, 3:20 p.m., 9:08 p.m. Now notice I'm using military time here on, or what we call military time, on the x-axis. So I'm converting 8:24 p.m. to 20:24 p.m. because 8 p.m. is really the 20th hour of the day, right? And 2 p.m. is really the 14th hour of the day. 9 p.m. is really the 21st hour of the day. So I'm converting those to military time, and that's my x-axis in time, and on my y-axis I have the height, or the tidal height, in, let's say, meters. So once this graph has been sort of sketched in, I can then calculate the period between given points. And again, I want to find points that are really easy and that we have data for. So I can find the period between the first two low tides, and that turns out to be 12 hours 27 minutes. I can also find the period between the first two high tides, and that's going to be 12 hours 13 minutes. Notice they're different. I can look at the next two low tides, 12 hours 17, next two high tides, next two low tides. Notice how they're all slightly different. So how do I choose a period? Well, I can take the average period that I'm seeing in the data. So really what I'm going to do is take the average of 13, 38, 27, 17, and 27, and that's going to get me an average period of 12 hours and 24 minutes. But now I really have to convert that into a decimal hour, right? This is 12 hours and 24 minutes. That's not really easy to put into my calculator, so I need to find out what percent of an hour 24 minutes is. Well, if I divide 24 by 60, I get 0.4, right? 24 minutes divided by 60 minutes in an hour, I get 0.4 hours. So my period is really 12.4 hours. Once I know this, I can find B. It's simply 2 pi divided by P, or 12.4. That's roughly going to be 0.507. Remember, A and D both come from the maximum and the minimum. Well, I know high tide occurs at 7.2 meters, let's say, and low tide occurs at 3.8. So to find A, I subtract the minimum from the maximum, and I divide by 2, and that's going to get me 1.7. For D, I add the two together, 7.2 plus 3.8 divided by 2, and that gets me 5.5. So the only remaining value that I need is C. And remember, C comes from M. M is the point that crosses the primary axis, which in this case is 5.5 meters. And when the sine curve is going up here. So I need to find the distance from this point back to the y-axis. But I can make another assumption here, and that assumption is that M is going to occur halfway between the first low tide and the first high tide. So what I can do is I can subtract the time of the first low tide from the time of the first high tide, take the average, and that's going to get me the time, the time of M. So to do that, I need to take, or the time of M is going to occur at 1/2 the time of the first high tide, which is 1429, minus the time of the first low tide, which is 7:57. So this is 1/2 6 hours and 32 minutes, which really equals 3 hours and 16 minutes. And again, if I convert, well, first I need to add this to the time of the first low tide, and that's because this time, this extra time that I'm finding is sort of this distance right here, but I need to go all the way back to the y-axis, so I need to add the time of the first low tide as well. So M is really going to occur at 7:57, the time of the first low tide, plus 3 hours and 16 minutes, which is 11:13. Now again, if I convert 13 minutes into hours, like I did above, this will be 11.22 hours. This is when M occurs, at 11.22 hours. So this is C. Therefore, my final model is going to be T equals, H equals A, or 1.7, sine B, which is 0.507, T minus C, which is 11.22, plus 5.5, which is D.